think it's about time to get started. Welcome everyone, and thank you very much to Rosie Zhao, our speaker today. Um, Rosie is at Harvard University, and she'll be presenting a talk on RL-based fine tuning, which I at least am really excited to see. Rosie, do you prefer if people ask you questions during the talk or hold them to the end?
Oh, feel free to interrupt. Yeah. Um, I can't promise I'll see the chat, but if someone could also keep track of the chat, yeah,
Yeah,
just feel
I
free to
will.
interrupt me.
Yep, I'll keep track of the chat, and uh, thank you very much, and yeah, take it away.
Cool. Thank you, Mark, for inviting me, and thanks everyone for attending this talk. So I'm super excited to talk about some of the research that my collaborators at Harvard University and I have been doing in this very fast-paced, rapidly developing space on reinforcement learning-based fine-tuning. Um, two. Why? Maybe I should have tested that I can scroll. Okay, there we go. Okay, so before I get into kind of the specifics of my research, I just wanted to give a brief overview of this space. So this word post-training kind of broadly refers to some phase that comes after pre-training. There's also a mid-training phase that has kind of emerged, but we won't talk about that. So post-training basically adapts a pre-trained language model that has already been trained on a very large volume of data, think like the scale of the internet, to specific domains by further training on some sort of targeted data set. So some of these use cases include like getting the model to better follow instructions, specialize to specific domains, or adapt to like some target behavior, such as producing less toxic responses. And this is really the process that kind of turns your model from this sentence completion engine to something that works on a particular downstream use case or product. So what are the techniques that people kind of apply in this post-training phase? So one of the earlier techniques that was very popular is instruction fine-tuning. And the goal here is to kind of make the pre-trained language model imitate human or expert behavior. So the process is in this figure. So basically your training data consists of prompt as well as these like standard tokens. And we perform something called like teacher forcing, where you basically feed both the prompt and these gold standard tokens into your pre-trained language model. You obtain the next token probabilities conditioned on the prompt and these gold standard tokens, and then you do your typical negative log likelihood loss and do kind of this supervised fine tuning in this way. The caveat for this process is that you have to have these gold standard tokens, and these are typically very expensive to acquire. You need both like high quality as well as diverse annotations. However, supervised fine-tuning has shown a lot of success, particularly when paired with synthetic data generation, which is less expensive than getting human annotators to generate these gold standard answers. And so one example of this is the Newman Math data set, which consists of 860K questions that a large volume of that is questions that have been synthetically generated from existing data sets like math. And they showed that you can actually gain quite a bit of performance just by doing SFT on their kind of chain of thought that was, I think, you used like GPT-4 or something to generate some of these answers. However, it does seem that there's some sort of like performance ceiling with supervised fine tuning. Intuitively, just given the loss function, the model kind of learns to imitate like the style of the demonstrations. There's also this data quality and coverage bottleneck. So like I said, you do need like a large volume of these high quality demonstrations. And some people have even shown some of these like desirable reasoning behaviors, like backtracking, for example. If you try to kind of get the model to learn that in like a supervised fine tuning way, it kind of just learns to like imitate the backtracking without actually demonstrating the true capability. In comparison, reinforcement learning has kind of emerged as this very popular post-training technique. And very famously, DeepSeek, when they released like R1 back in January 2025, it kind of took the world by storm. They showed that on the left, this plot is DeepSeek R10. So this is just doing RL directly on top of the pre-trained model, like without any type of instruction tuning before applying RL, and still gets like very significant gains in performance, and famously had like very cheap inference costs. So the NVIDIA stock dropped like very quickly after the release of R1. But I think those fears have been kind of like washed away ever since then. I think like RL compute is kind of just continuing to scale up more, as evidenced by some of these companies kind of building larger and larger data centers. And these images are from a talk by Dan Roberts at OpenAI. And he basically said that although for the current models, RL compute still like this cherry on top compared to pre-training, they want to scale RL so much that like pre-training actually becomes a cherry in comparison, which is kind of really crazy to think about. And even like kind of the current version of these like so-called reasoning models that emerge as a result of this RL-based fine-tuning has like a lot more, like an order of magnitude more compute compared to its predecessors. So this area is only growing. And so I think there's like a lot of importance in really like understanding what's going on and kind of what are the best practices in this space. So just to be clear, like what is reinforcement learning? What does reinforcement learning fine-tuning look like? So in this case, our training data can only consist of prompts. So we don't need these gold standard tokens. But for reinforcement learning, we do need some sort of like reward signal to then maximize. And something that has emerged as very popular is actually using so-called verifiable reward signal. So in domains like math and coding, you can actually verify the language model's completions for correctness. And then so this is actually used as a reward signal that is then optimized for with these like policy gradient based methods. So just to be clear, like what are the key differences between supervised fine-tuning and reinforcement learning based fine-tuning? So given some sort of like input prompt, as well as a gold standard answer, we can also generate some sequence by our language model given this input prompt. And so for SFT in this first bullet point, like I said before, the update uses the gold standard completions Y star at every time step. So we call this like teacher forcing. Whereas for reinforcement learning based fine tuning, now our loss function is determined using the model's own completions, but the update is kind of scaled by the reward. So if you have a higher reward, this objective will kind of upweight the probability of outputting this distribution that came from the model itself. If it's a low reward, it will kind of, the probability mass will get shifted elsewhere. And yeah, this is just technicality, but this update rule uses like reinforce without something called a value function baseline, which is present for a lot of the popular algorithms used in this space, like PPO or GRPO. But this is kind of the main difference between supervised fine-tuning and reinforcement learning-based fine-tuning. Are there any questions about kind of the basic background for these algorithms before I continue?
Now, Rosie,
Okay.
I'll just say that this is a absolutely fantastic overview. I've seen a number of these type of things on like
Mhm.
a quick introduction to post training, and so far, yeah, I really really like this. Very easy to
Thank you.
follow, and you're covering everything quite well. So thanks.
Thank you. Okay, great. Um, yeah, so I guess there have been a lot of investigations in this RL-based fine-tuning space to kind of discuss, really like investigate what's going on. It seems like one thing that has really emerged is that the performance and the behavior that kind of emerge as a result of reinforcement learning-based fine-tuning really depend on your pre-trained model. So these plots come from this paper from Noah Goodman's group, which kind of investigates certain phenomena that DeepSeek R1 reported emerged as a result of their fine-tuning. For example, like these type of like aha moments or kind of evidence of like backtracking. This task here is like countdown. And basically this paper shows that like depending on your base model, some of the phenomena can be reproduced and some of it can't. So for example, like increased response lengths during training, so longer and longer chains of thought, as well as like a significant increase in score was kind of observed for Quen, but not so much as for Llama. But if you do some like sort of continued pre-training on top of the llama models with some of this like curated math data that might have had a bit of like backtracking in it, then reinforcement learning kind of emphasized this. So pre-training data set really does seem to be the significant hidden factor. And it's just kind of unfortunate that this is like the one thing that is kind of universal across all the technical reports that these industry labs kind of publish, that this is like the one thing that they don't disclose. So through the research that I'll be presenting this presentation, I want to claim that understanding reinforcement learning-based fine-tuning actually requires us to look back at pre-training. So how can we explain the success of reinforcement learning-based fine-tuning through the lens of pre-training? I'll actually be covering two papers. Kind of one was a follow-up for the other. And so the first paper kind of shows that reinforcement learning-based fine-tuning upweighs so-called like best distribution from the pre-training data to solve a given task. The second work actually shows that to some extent, the best distribution can actually be set by your initial tokens in your generation. So we kind of propose this method called prefix RL, which only does reinforcement learning-based fine-tuning on the prefix of the generation. I'll get into more details when the time comes. But yeah, so these two contributions come from the following two papers. This first paper called Echo Chamber will be appearing at Column this year, and then Prefix RL currently a submitted preprint. So yeah, I'll cover these two papers and then kind of wrap things up with this broader discussion about kind of current trends and like related ideas currently going on in the literature. Okay, we'll cover first paper. So again, yeah, this is a really saturated space. As a researcher, PhD student in this space, it's often very overwhelming because there's just like always some new paper every day doing a new investigation or presenting some algorithmic improvement. So whether it's like about these aha moments, how to encourage better and long chains of thought, a lot of spin-offs like DAPO, Dr. GRPO, SPPO. There was that day on Twitter where someone did reinforcement learning with random rewards and managed to get performance improvements. So there's like a lot of investigations in this space, but the conclusions really vary widely across different base models. Seems like pre-training data really is the confounder. And so even on these downstream benchmarks, the performance like widely varies. And for example, this work on doing reinforcement learning with random rewards, I think a lot of follow-up investigations have shown that this is kind of a result of both the base model being Quen, and also there's some sort of bias that the RL algorithm, which they use GRPO, actually introduces to the policy gradient that actually kind of biases the process to kind of encourage like better generations for Quen specifically. So for us, like relative to the other works in this space, we wanted to kind of take a different approach where we actually study reinforcement learning based fine-tuning behavior by actually pre-training our own models from scratch. So we can actually control for the data mixture and we know like exactly what the model is kind of exposed to before the fine-tuning process. So this lets us really study the effect of the data mixture, the model size, as well as the choice of RL algorithm and different hyperparameters. So our exact pipeline is as follows. We basically pre-train 150 million and 1 billion parameter models using the OLMO code base. I'll get into details on what like these pre-training data sets are. But after we obtain these pre-trained models, we then perform RL-based fine-tuning on the GSM-AK trained dataset. So our dataset for RL looks like these grade school math problems, as well as some gold standard answers. These are like 7.5K examples. And then we'll perform evaluation using the GSM-AK test set. We have a bunch of analysis there that I will get into. Before that, like what do our pre-training data set mixtures look like? So because of our limited compute, we have like kind of relatively smaller models. So our pre-training data mixture kind of includes data sets that are kind of focused to the mathematical domain, particularly related to GSM-8K. So the main data set we use is kind of like akin to these large like pre-training corpuses. We use like 53 billion tokens of kind of general math. So these tokens are sourced from the fine math data set as well as the algebraic stack subset of Profile 2. And so these are like tokens that are related to math that come from like archive papers, for example. So along with this main pre-training corpus, we also include some of these like instruction data sets. And so these data sets are all kind of synthetic augmentations that come from GSM-8K as well as math. So we focus on 3 different data sets, and we basically can kind of add like different amounts of these data sets in our mixtures. So I'll go through each of these data sets. So the first one is TinyGSM, which consists of almost 3 billion tokens. And the reason we pick these data sets is that there's kind of a specific format to the generations, like the answers given to these questions that we can then kind of track in our own models generations. So we can actually see like where the model's resulting generations are sourced from. So in the case of TinyGSM, all the answers are given in a code format that have this Python function signature simple math problem. It kind of returns the result that answers the original problem. The second data set is Open Math Instruct 1, and these are generations coming from Mistral, I believe. And the generations from Open Math Instruct 1 also use Python code, but they're kind of delineated by these XML tags. And then it actually also produces kind of like an output to the code that it writes. And the third data set we use is Open Math Instruct 2, which is a lot more tokens. And these are generations from, I believe, the Llama 400 billion model. And these generations are pure like natural language. So this is just your regular chain of thought with like a boxed answer at the end. Um, so yeah, so these are the 3 data sets we focus on. And again, these were kind of chosen because they have like certain characteristics that we can very clearly track in the model's generations after pre-training as well as like during reinforcement learning based fine-tuning. Yeah, so these coefficients I had in the previous slide basically just are the amounts of each data set that we include in pre-training. And depending on what our mixture is, it was clear that this can kind of control the behavior of the model after pre-training. So below I have these 3 plots that kind of evaluate the pre-trained model on different data set mixtures on the GSM-8K test set. And then we kind of search for those different qualities that I mentioned. So this like def simple math problem for GSM, TinyGSM, the XML tags for Open Math Instruct 1, and then Open Math Instruct 2 is kind of the only like text-based chain of thought data set. So kind of lump like Open Math Instruct 2 generations into or we kind of lump all the model generations that aren't these like code-based ones into text. And you can see that depending on our mixture, so on the left is TinyGSM and Open Math Instruct 1, or we increase the amount of Open Math Instruct 1, or we add Open Math Instruct 2. After pre-training, the kind of quantities of the model's generations from each source does vary. And so our goal is kind of to track these quantities and how it kind of evolves during the reinforcement learning based fine tuning. Okay, so now I'll kind of go into tracking some of these quantities during reinforcement learning. So the data mixture we have as an example is one times TinyGSM and kind of 4 copies of Open Math Instruct 1 and no Open Math Instruct 2 for now. So I'm going to flash 2 plots. All right, so let's focus on the left plot for now. So the x-axis here is samples. So this is on a log scale, and this is kind of like the number of samples seen throughout all of RL-based fine-tuning. And this plot is tracking the distribution of the model outputs generation. So it's like that bar chart that was in the previous slide, but kind of just tracking across different checkpoints during RL fine tuning. And so the main thing here that is very stark is that like the output distribution kind of converges to the tiny GSM format. And notice that like the x-axis is on this log scale, so this actually occurs like within the first pass over the data during training. So very quickly, the model kind of learns to amplify one sort of output distribution. And interestingly, this isn't the distribution that kind of occurred the most often, which is Open Math Instruct 1 at initialization. The right side is this showing accuracy results, so both global as well as per format style. So the dotted lines show pass at 1, majority at 64, as well as pass at 64 performance. And we do see like overall in pass at 1, we get almost like a 20% boost. There's a slight increase in the majority performance, and pass at 64 largely remains like the same. And you can see like the accuracy of the tiny GSM style generations also increases along with overall accuracy. Um, these other solid lines are a little bit misleading because this corresponds to like a very, very low fraction of the actual model's generations. But yeah, so this is like one instance where the RL-based fine-tuning kind of selected the best performing distribution at initialization. So Tiny GSM here kind of had the best accuracy on the eval set at init. Yeah. So this is now with like a different data set mixture. So we doubled the amount of Open Math Instruct 1 that we had in the previous slide. And let's see like kind of what happens as a result to the percentage of the generations as well as the accuracy. So in this case, we see like the same phenomenon in the sense that the RL-based fine-tuning amplifies one distribution, but here the kind of initial percentage of the Open Math Instruct 1 style generations is so great that this is like the eventual kind of output format that the model converges to. However, if we look at the accuracy results, it actually kind of collapses. So there's some kind of progress being made, but then near the end of training, there's actually some sort of collapse. And we actually end up with a lower performance than at init. And so we call this like kind of a failure case where RL actually amplified the lower accuracy distribution at init because just of the high prevalence of the Open Math Instruct 1 style generations. So this is just kind of more evidence that like the pre-training data mixture really does matter. And this doesn't seem like such a big difference to incorporate so much Open Math Instruct 1 data. So this is like one of the findings from the paper. Are there any other questions about these two sets of results so far?
So I think this is a really interesting set of results, and although you were, I think, the first one I saw on with it, I've seen similar results replicated in other papers since, and
Mhm.
I want to ask, why do you think that this, like in, so I believe that from your results that what it seems to be showing is that the reinforcement learning is sort of sharpening the probability distribution around
Mhm.
hopefully a correct set of answers, but it's not actually
Mhm.
learning their behavior. But that
Mhm.
really contrasts to what we see in playing games like Go, where AlphaGo achieves superhuman performance famously. So, do you think that that's because like the distribution space of Go moves is smaller, so even an infinitesimal probability gets sampled occasionally? Or is it something to do with the self-play aspect? Or do you have any sense of why that would be?
Yeah, it's a really good question. I think like there's some differences between kind of the RL-based fine-tuning applied for language models compared to something like AlphaGo. In particular, like we're kind of just like the exploration being done in this RL-based fine tuning is done on like a token level. And I think like this kind of will become like a recurring theme through the talk, but I think like token level, like it just like expecting the model to be able to explore in token space, even with like high temperature sampling or with like low KL coefficient doesn't seem to be like sufficient. There is I think like also a lot of recent works in this space have shown that this limitation of the RL-based fine-tuning that's dependent on your initialized model output distribution. And so like I think to really harness a lot of the RL-based fine-tuning kind of and like the success that AlphaGo has kind of exhibited, there has to be some more like explicit exploration bonuses, it feels like. Um, I think I wanted to say something else. Yeah, another thing is that something that we observed that other papers have also shown is that like here, like the accuracy is kind of progressing still like late in training. But I think if you look at specifically like the certainty of the model and like entropy, for example, this gets sharpened like very, very fast during RL-based fine-tuning. So I think like what happens here is that the model just becomes too like locked into the open math and struct one style outputs at the very early phases of training. So it can't really like do this exploration. So there's like this constant tension between like kind of amplifying like what you see early on that gets you a decent reward, as well as still being able to like explore later on. So a lot of these like explicit like entropy regularizers have been also emerging in the space.
Thank you.
So yeah, I have some other results. So yeah, we have kind of like a kind of array of results from the paper. I'm just like summarizing a couple of them here. Another interesting thing is that you can kind of in our controlled setup, you can very clearly see the effect of like the KL coefficient. I think before people were saying like, oh, you can like set KL to 0, and it would still like work. I think there is like a difference between using a high and low KL coefficient. So with the high KL coefficient on the right, it actually does kind of constrain the model's output distribution during RL-based fine-tuning, kind of keeps it like relatively closer to the distribution at initialization, but there's still this like amplification behavior still going on. Whereas for like low KL coefficients and KL equals 0, we also have in the paper, it kind of amplifies like very fast. Um, last thing, we also kind of wanted to see like if we only pre-train on like uh, one of these instruction data sets, is there still improvement from reinforcement learning based fine-tuning? So we basically vary the quantity of tiny GSM in the pre-training, and then we do RL on top of that. So on the left, we kind of track these pass at 1, pass at 64, majority at 64 metrics across different amounts of tiny GSM. We see that more tiny GSM kind of just like improves performance. And then on the right, this is each line is different quantities of tiny GSM tracked over the course of RL-based fine-tuning training. And we do see that there is like a difference in the improvement. So RL performance improves like even on a single distribution. Um, we did like investigate this like a little bit further, like what is then RL actually like kind of sharpening in this case where there's only like one supposed output distribution format. Um, and so we found that it actually kind of amplifies certain like stylistic biases in the RL-based fine-tuning. So one thing we did observe, for example, is that there's kind of always this doc string in the tiny GSM style generations that kind of repeats the question, for example, inside of the doc string. And so I think at init we kind of tracked if uh, if we kind of only put like a substring of the question and we kind of include more and more tokens, like what's the success probability of the generations in that case? And basically, if we included more of the question, the success probability was actually like going further and further up, just doing some sampling from this generation. And then so we tracked some of these kind of like stylistic qualities of the gold standard tiny GSM generations across RL-based fine-tuning. And so we were actually seeing that, so in this case, this is for 4 times tiny GSM. On the right, we were tracking certain things like matching a doc string or like kind of very specific qualities of the generations, and these kind of do get amplified across the course of training. So, and these also kind of adhere more closely to kind of like the gold standard tiny GSM generations that it saw in pre-training. So there is still some sort of like sharpening within an output distribution during RL. It's like unclear like why this kind of leads to some increase in performance, but it's just kind of like more consistent formats. Yeah. The last thing I just wanted to highlight is that we also showed there's like a scale dependent bias, it seems, in terms of what the output distribution is converged to. So in this case, we have like a 1B model, and this data mixture is kind of 1x of each data set. And so um, for the same, we have the same generation and accuracy results. And I think the interesting thing here is that actually what gets amplified is the text or like the natural language type of generations. And so during RL, the 150M model kind of sharpened to the tiny GSM style code, and the 1B model sharpened to kind of more natural language chain of thought. And this actually was consistent across multiple seeds. So we kind of hypothesized that like the 150M model is quite small and the tiny GSM style format is much simpler with like the lines of Python code. So I think it kind of more reliably like doesn't make these like small errors that might lead to like compilation errors or something when we verify the code automatically. And this kind of led to a different distribution kind of being amplified. So the 1B model actually could reliably output natural language chain of thought. And so this is the resulting distribution got amplified. So we have like a lot more kind of investigations on like the RL algorithm as well in the paper, and also a bunch of different mixtures. But just to summarize, kind of this controlled setting, like even though these are on like smaller scale models, still led to different insights about the RL-based fine-tuning process. So in particular, the effect of the data mixture. RL typically does converge to like the best performing distribution, which kind of intuitively makes sense given that the objective of RL is to maximize the expected reward. But there are failure cases where you have kind of an initial low probability for this best performing distribution. So more along this line of kind of RL being limited by what your model initialization output distribution is. In terms of the model size, it seemed like different model sizes can prefer different strategies. So code versus text. And we also had some effects on different hyperparameters. So the KL term in particular, for example, keeps some sort of mixture distribution without hurting performance. Um, and yeah, I think this is also kind of like a recurring theme about kind of like KL and these like entropy regularizers affecting the model's output distribution through RL training. The last thing that we did also have in the paper that I haven't mentioned here is that we did see some sort of transfer from like GSM-8K to other math domains, like math data sets like Math 500. So I think our 1B model obtained like almost 10% improvement after doing reinforcement learning-based fine-tuning on only GSM-8K. One thing to note though is that like Math 500 isn't quite like fully out of distribution for our pre-trained models because Open Math Instruct 1 and 2 do have kind of these synthetic questions that were seeded from both GSM-8K and math. So technically this is like out of domain after doing RL on GSM-8K only, but there is still some sort of familiarity with like math style questions from pre-training. So kind of also highlighting again the importance of kind of showing some of these examples in pre-training, even if you aren't like explicitly training on more of these like in-domain examples in the RL-based process. Okay. Yeah, are there any questions about this first paper before I go into the second paper? Okay, cool. So the second work is kind of this method that's motivated by what we were observing in this first paper. And this is, we call it prefix RL, parameter efficient RL using prefix optimization. So yeah, given the first work, we can maybe if we presume that RL-based fine-tuning is roughly just kind of reweighting the support of the output distribution of the initialized model, um, we can actually like maybe take this like one step further, where like actually maybe the first few tokens can actually decide the solution format and the strategy. So this is what we were seeing in the first paper, where um, given like the tiny GSM, the open math and struct1 style formats, we didn't actually observe like any sort of like mixing between the two distributions. And a lot of these like kind of defining properties like the Python simple math function signature or the XML style tags kind of like locked it into that distribution format. So we were seeing some of these kind of trends also in like these open source models. So for example, like Olmo actually does sometimes for math problems have the same function signature. I think llama style models kind of seem to want to like delineate its process into like explicit steps. Um, and then Quen and like DeepSeek kind of seem to like start by kind of summarizing the problem and kind of delineating its like overarching strategy. So we thought that maybe we can actually like exploit this. So if it does seem that RL is picking some pre-existing style and just amplifying it, and moreover, this can be kind of determined by the first few tokens of its generation, then we can actually train a small adapter model that kind of selects this style, but just generating a prefix. And then we can actually leave the base model frozen. So this is a very like conservative alternative to full RL-based fine-tuning, where the small adapter kind of acts as this like strategy or style search, and the base model kind of just completes the reasoning from there. And so prefix RL in this case, basically given the same like pre-training data, now we have some adapter policy that's typically like a very small model that generates only the first couple of tokens of the answer before it is fed into a frozen base model that can be a much larger model that generates the rest of the completion. But the reward signal is based off of these two generations combined. And then it is just the adapter policy that is actually updated. So yeah, so prefix RL is basically the adapter is generating prefixes that are then completed by this frozen base model, and then only the adapter gets updated. Before I jump into kind of like our main results, one thing we wanted to kind of test before doing this is that is like RL actually kind of boosting the performance because the model truly is reasoning better, or it's kind of like nudging the model just towards like a more effective formatter strategy. So on the left plot, we basically set the base model to be the same as the adapter model. So the model itself is kind of completing its own generations, but we're only doing RL on the first 16 or 32 tokens that it's actually generating. And so full RL got like a 10% boost in performance, whereas just training on the first couple of tokens gave only a 6% boost, but like 16 and 32 tokens is really like very small. So I think it's surprising that actually if you just optimize this small number of tokens, it does recover even 50% of the gain you get from doing like full RL-based fine tuning. Um, and so like, okay, like why would we do prefix RL in the first place? So one thing is that it really does significantly reduce your training budget in terms of flops. So I have kind of in this table comparing full RL based fine tuning with prefix RL, where you only optimize for the first K tokens. as well. So this is like training and inference compute. And so, yeah, big T is kind of the number of tokens you're generating per rollout, and capital R is kind of the total number of rollouts seen during training. So you can see that the training budget is kind of reduced by a factor that's proportional to the number of parameters in your big model times T divided by the number of parameters in your small model times K. So in our setup, if we're using like a 1B adapter model for a 7 dB base model, with these number of prefix tokens and 2048 tokens per rollout, you can actually reduce the training budget by like a factor of 5,000. So even if you don't like obtain maybe as significant amount in performance as you would have for the full RL-based fine tuning, if you're resource constrained, this can actually let you kind of do RL on the base model. With like still some sort of like gain in performance. So along with reducing training budget, like prefix RL also, like I said, requires much less computational resources. So we could do RL on a 1B adapter model with like 4 GPUs, and you can just use some API for inference, whereas you would need like a lot more GPUs to do like full RL on some 7 dB model. And also there's like a lot of cases where full RL is just like not possible on the base model. So quantized models is an instance where we actually saw quite a big boost in prefix after doing prefix RL, which I'll show on the next slide. But also like for huge models as well as closed weight models, you could actually also kind of leverage prefix RL. And so we did have some experiments in the paper where we were trying to actually like try and improve DeepSeek or GPT-4o mini performance just with this like prefix training method. Um, so kind of like across the board, we do see some performance gains from prefix RL just by like generating the first 32 or 64 tokens that are then fed into the larger model. So sorry, this plot is like a little bit hard to read, but basically the titles are the base model fed into the adapter model and then the data sets evaluated on. So a lot of our like biggest performance gains were actually shown on these quantized FP8 models. Um, and so yeah, the paper, like the preprint will come out soon on arXiv, but we did see like consistent improvements across model scales as well as test benchmarks. Um, oh, there's a hand raised, sorry.
Yes, I had a question. So, what is the motivation in the intuition for me to see like how k equals 32 performs sometimes better than 64? The second row, first column, for example.
Um, yeah, I think there is kind of like maybe this limit of the like adapter model to some extent. Like um I think there's some way that like generating like a larger prefix with this like much smaller model, in this case it's like 1B versus 72B, kind of like locks the larger model into a certain like perhaps like reasoning like uh like I think maybe perhaps like at 64 tokens you're kind of already starting like the solution to an answer, and maybe if the model like the 1B model is just like not powerful enough, it could kind of start off with some wrong chain of thought that can then maybe limit the performance of the large model.
I see. So if the number of parameters of the model increases, uh, what do you think we would see? Because I think this phenomenon is, as you said, related to the number of parameters of the original model.
Yes. And yeah, I think like it's related to parameter size difference. It's also related to like model, kind of actually model-based family. So kind of in the previous slides, I was showing that like depending if you're like Llama or Quen, like Llama seems
Hmm.
to kind of output like step by step versus Quen kind of starts off with these like overarching summaries. So I think we showed in the paper that you actually, if you have like differing model families between the adapter and the base model, you actually might want to do some sort of like SFT phase to kind of align the output distributions of the two models in some way before training. So we were seeing this particularly with like trying out with like the closed weight models. And it is like much harder to kind of get any sort of performance boost on like the closed weight models because they're already pretty good on these benchmarks. So
Right.
yeah, I think like it's both difference in parameter as well as
Hmm. Yeah. Yeah.
base
And
model
also
family
primary.
difference.
Yeah.
Yeah.
Okay. Thank you very much.
Yeah, I think it is interesting. I think that there is kind of any performance gain in the first place because this is like very few tokens. Um, I think I'm just gonna oh shoot, I lost my train of thought with this. Um, I think yeah, sorry. I think some people have actually been showing uh like depending on how you actually feed the prompt into your model, like this can also obtain like very differing performances. So I think there was like a recent work that actually showed like a lot of the performance gains you get from like RL and Quen, for example. If you just do like enough prompt optimization, you can actually obtain like the same performance that the Quen model obtained like after RL-based fine-tuning. So more along this question of like, is RL doing something really more than what the model kind of already had the potential of doing during pre-training, which I think is like a really hard kind of problem to be exploring just because like the space of like output distributions is so great. Yeah, and then so yeah, I guess um in this we also have some like examples of what the base model kind of began to generate after RL-based fine-tuning. And so the second column is kind of the uh, generations from like the base model before prefix RL. And then the third column is after prefix RL. This is actually what like the 1B model kind of learns to generate. So it kind of does learn to kind of mimic some of the formats. And it's like very subtle differences that still led kind of could flip the answer from the base model from incorrect to correct. So again, like I think exploring like the space of output distributions and how this kind of affects like downstream performance on these base models is, I think, highly non-trivial. Yeah, and so this is kind of another difference that I was mentioning between the different base family models. So on the previous slide, the base model was llama, and here the base model is Quen. And so the kind of what is learned during prefix RL is actually quite different across these two different models. Yeah, so I just wanted to, okay, yeah, we have, it's 53. So I just want to wrap up with some final discussion. So yeah, I think like across these works and also in the current literature, there's kind of these like two contrasting views. And so first view is that like reinforcement learning based fine tuning is really just like distribution sharpening or kind of like brings the output distribution to like kind of the prompt space that we're using when we're evaluating these models. And so we did have evidence of this in our work where we were seeing that like pass set 1 was improving, but pass set 64 was like not improving and also sometimes decreasing, kind of along the lines of like RL-based fine-tuning is kind of hurting the model's output diversity due to this kind of distribution sharpening. The other view is that RL really is doing something more than distribution sharpening. One thing is that like prefix RL did not recover all of the full RL performance. So it's not just like the prefix that can kind of harness all of the performance gains that RL can bring. And also there were kind of some other papers and some other investigations we did that like maybe full RL can actually solve new problems. So this is just like a plot from our pre-trained model, our pre-trained 1B model, and this is like before RL and after RL. We were looking at like actually given 64 generations per problem, how many of these generations were actually correct. So this first bar is like the number of questions that had like 0 generations correct. And like this does go down during training. And interestingly, it kind of settles in some like bimodal situation where like there's also a peak at all the generations being correct. And like it's possible these 64 generations have like some duplicates or something. So kind of this distribution sharpening. Um, but then I guess like on Math 500, for example, like the pass at 64 like was not really increasing that much. And so a lot of the problems that had like 0 generations correct did like not a lot of this mass actually moved during training. And actually most of the mass that was moved is actually just certain problems having more generations that were actually correct. And there have been like other papers, like the Pro RL paper that came out from NVIDIA that kind of showed that there are certain like out of domain benchmarks where the base model couldn't get like the correct answer even after like pass at like 1,000 or something. Um, and so like it's possible that the data set that you choose during RL-based fine-tuning. In all of our investigations, they're all kind of like in domain within this like mathematical reasoning, but they kind of test on like a much wider variety of domains. So there's like a lot of questions about like the influence of the data and the influence of the algorithm in terms of what RL-based fine-tuning can harness from the base model. Um, but I think like definitely the main message is that the pre-training data really does heavily impact the RL-based fine-tuning performance. So I think a lot more investigation should go into kind of what is the effect of like what the model sees during pre-training on the downstream RL performance, and is there some like optimal way of kind of like priming your model for doing RL. So yeah, some open questions are like what pre-training data actually enables successful RL-based fine-tuning. So some of the potential factors include like the frequency of the target behavior, kind of diversity of generations. So you don't want to, for example, do too much like supervised fine-tuning on the base models. People have shown that this actually limits like RL performance because it kind of like locks it into one sort of format or output distribution. But there might be some work there that actually kind of identifies like what's like an optimal pre-training data mixture to then enable like the biggest performance gain during RL. And the other main open question is like, can RL-based fine-tuning actually push the model outside of the initialized model's support? So the ProRL paper, as I mentioned, showed maybe like if you do RL on these like out of distribution data sets. But I guess there's also this question again of like, can the model just obtain that same performance just by optimizing the prompt? So they show that like past that 1,000 performance really does increase as a result of their RL-based fine-tuning, but it's also still unclear like if you were to take like the most cynical view of this result, like maybe if you just tweak the prompt somehow, there's some output distribution that does lead to the model solving the question. And I think there's even more evidence of this now given, I don't know if people are familiar with the IMO gold results and that paper that came out that showed that for Gemini, you could actually obtain a gold medal just by giving it the right system prompt. So I think there is a lot of questions to kind of explore in this space. And again, like I mentioned before, something that could be very promising is actually smarter RL algorithms with very explicit exploration bonuses. There have been some like very recent works kind of on this trade-off between like entropy and performance gain in RL. related to this like token level exploration. So some way of actually baking in explicit exploration bonuses similar to the classical RL literature, I think is very promising. Yeah, that's it. So thank you so much for listening to my talk. I have to give credits to some amazing collaborators at Harvard, as well as our professors like Genghis and Sham. So yeah, thank you for listening.